Hi everybody and welcome. Today we're going to be talking about independent events in our first video, and then in our second video we're going to be talking about conditional probability. So to start off, we're going to go through a definition, some examples, and take it one step at a time here. So independent events we define these as the probability of one event in no way affects the probability of the second event. So an example of an independent event would be you flip a coin and you roll a die. If you flip a coin and it lands on heads, that's not going to affect what the die lands on, right? So the idea here is that event number one doesn't change the probability of event number two. It's not, I think, like, unless there was some like special magnet inside of the die that was like, oh, the coin landed on heads, that means I must be a 5 now. That basically doesn't happen, right? So the idea is that when you roll the die, it's going to randomly be whatever one of the 6 numbers it was going to be, regardless of the outcome of the first event. A non-example would be you, let's say, draw a 10 from a deck of cards, and then you don't replace it, and then you try to draw a 9. If you're looking at the probability here, in the first event, there were 52 total cards, and 4 of them were 10s. In the second event, the reason why this is not an independent event is because we now have less cards. So the probability of drawing a 9 changed because you literally took one of the cards out of the sample space. So it fundamentally changed what you have there. So there's still 4 9s in the deck, but in this case we see that instead of having 52 cards now, we just have 51. So today we're going to be focusing on this example where the probability does not change, but it's important to know and to consider those non-examples of things that do affect each other. So, for example, a question they might ask you is, what is the probability of drawing an ace from a deck of cards, replacing it, and drawing a second ace? So basically the probability of getting 2 aces. So the probability of getting an ace is 4 over 52. You take that card, you put it back, and then you multiply it by the probability of getting an ace again, which in this case is unaffected. It's an independent event. So now you can go through and calculate. So we'll have 16 on top, and then 52 times 52 on the bottom. Get us 2704. So this probability, if we put it into a percent, would be, or as a decimal first, 0.0059, which is actually 0.6% if we round it there. So very, very unlikely to draw 2 aces in a row. All right, so again, the idea here, denominator doesn't change. The probability of these 2 events don't depend on each other. A second probability would be, let's say, 90% of students love winning. And we're going to say we randomly select 3. What is the probability that they all love winning? So in this case, we would calculate our probability of loving winning by taking the number of students that we have in our geometry class here. So we'll say out of 15, 13 and a half, sorry, would be the correct probability. So that's 90% of 15. Then we'll do it again. And then we'll do it again. So we would basically just be going across and multiplying, multiplying, and multiplying over and over and over again to get a decimal answer here of about 73%. So we're basically just taking the probability of the first event, multiplying it again, multiplying it again. And in this case, we all have the same probability because we all love winning, or 90% of us do. The other 10% are probably going to fail the class, so sorry. But that's the idea for independent events with probability, is you just take each of the individual events, you take the probability that you love winning, and you multiply it by the probability that you love winning over and over again. And the idea here is that this probability does not change based on the event before it, and that's what makes an independent event. So basically for these, to recap, multiplier probabilities and the probabilities also don't change. So as a final summary here, the way that we write down this notation, this is our multiplication rule, is the probability of A and B equals the probability of A times the probability of B. And in this case, we can also call this, sometimes you might see this written on the state test, as the probability of A and the intersection of B. These two things basically mean the same thing. So for your all intents and purposes, you can use this formula. So again, that upside down U on the bottom, it just means intersection. It means where we have both A and B together. So either way works.